Somewhere out in the dim reaches of the cosmos, our tiny planet turns quietly in the light of its star. From our first steps on solid ground to our first flights beyond it, humanity has pushed through challenge after challenge. We've survived ice ages, plagues, and wars. Yet the future remains an open mystery. What lies ahead for us? Which possibilities might one day become real? Tonight, in this stillness, let's drift into the darker future scientists have imagined. Not to frighten ourselves, but to understand, to reflect, and to appreciate this very moment. Let this gentle voice guide you through distant possibilities as the night wraps around you and sleep draws closer. If these calm stories of science bring you comfort in the dark, stay with us. Let this channel become a quiet companion whenever you need rest. Subscribe, if you'd like, and let the universe's mysteries softly carry you into your dreams. Imagine a morning 4,600,000,000 years ago. No one was there to witness it, no eyes to see it, but inside a swirling cloud of dust and gas, something began. Gravity pulled tiny grains together. Pressure rose. Heat climbed. And then, in a miraculous flash of physics, hydrogen atoms started to fuse. Light burst forth. Our sun was born. From that moment on, this star has shone without rest. Every second, it turns about 4 million tons of matter into pure energy. That light streams out in every direction, and a tiny fraction, just a sliver, lands on the small blue world circling it. That light warms the oceans. It feeds the trees. It paints our sunsets and sunrises. It is the reason we exist. But nothing lasts forever. The sun, like every star, has a life cycle. It rises from dust. It grows into brilliant radiance. And one day, in a distant future, it will die. Not tomorrow, not in 1,000 years, not even in 1,000,000. But in billions. The transformation will come, and when it does, everything we know will change for good. This is not a scary story. It is a story about time, about the patience of the cosmos, about how everything has a beginning and an end, and how beauty lives in both. So pause for a moment. Take a breath. Feel the sunlight, whether from memory or imagination, and understand that it has been here for 4 billion years and will remain for billions more. Right now, the sun is in its middle age. Astronomers estimate it is roughly halfway through its life. Deep in the core, where the temperature reaches 15 million degrees, nuclear fusion never stops. Hydrogen fuses into helium. Helium accumulates. And slowly, very slowly, the star's internal structure shifts. In about 1 billion years, the sun will be roughly 10% brighter. That might not sound like much, but for Earth, it means everything. Temperatures will rise. The oceans will evaporate more quickly. Water vapor in the atmosphere will amplify the greenhouse effect. And gradually, the planet will warm. Life as we know it will have to adapt, move, or vanish. But that is only the beginning. 5 billion years from now, when the sun's core is nearly out of hydrogen, something strange will happen. The core will contract. Temperatures will climb. The outer layers, still rich in hydrogen, will ignite more fiercely. The sun will expand. It will become a red giant. Picture that. A star once small and golden will swell like a slow-growing balloon. Its surface will cool, fading from yellow to orange to red. But its size will grow monstrously. It will engulf the orbit of Mercury, then Venus, and then, maybe Earth. Scientists still debate this. Some calculations suggest Earth might escape direct destruction as the Sun loses mass and its gravity weakens, pushing Earth's orbit outward. But even if it survives, the planet will be a scorched wasteland, its surface melted into oceans of magma, its atmosphere stripped away by violent solar winds. No more blue oceans. No more forests. No more white clouds drifting across the sky. Only rock and fire and silence. But remember, This is 5 billion years from now, 5,000 million years, a span as long as the entire history of life on Earth. In that time, everything could change. Humanity might be long gone, or far away among new stars, or transformed into something we cannot imagine. So we do not need to fear. We only need to understand. And in that understanding, cherish the fragility and beauty of this moment. After the sun swells into a red giant, it will stay in that form for millions of years. Its surface will ripple and heave, like slow waves rolling across a vast cosmic ocean. The outer layers will be pushed outward by intense radiation pressure, and gradually, ever so gradually, the star will begin to lose itself. Imagine that, a star slowly dissolving. Not in a sudden blast, but in a long, gentle farewell. Its outer gases will drift into space, forming delicate, shimmering clouds. Astronomers call these structures planetary nebulae, not because they have anything to do with planets, but because through old telescopes they looked like faint, blurry disks that resembled distant worlds. These nebulae are among the most beautiful sights in the universe. They glow with ethereal colors, soft blues, greens, reds, and pinks, each shade representing a different element illuminated by the fading radiation of the dying star. Their shapes are intricate, sometimes round, sometimes spiral, sometimes like butterfly wings or enormous hourglasses hanging in space. And at the heart of every nebula, beneath all that beauty, lies the last surviving core of the star. The sun's core, the only part left once the outer layers drift away, will collapse into a tiny, incredibly dense object, a white dwarf. It will be no bigger than Earth, yet it will pack in about half the mass the sun once had. Think about that density. A teaspoon of white dwarf matter would weigh as much as a car. A white dwarf no longer burns fuel. There are no more nuclear reactions roaring inside. It simply glows, shining with the heat it has stored over billions of years. At first, it will burn fiercely bright, scorching hot, well over 100,000 degrees at its surface. But with no new source of energy, it will slowly cool. Millions of years will pass. Then billions. Then trillions. And slowly, very slowly, the white dwarf will fade. From white to yellow, yellow to orange, orange to red. Eventually, after a span of time longer than the universe has existed so far, it will become what astronomers call a black dwarf, a cold, lightless ember drifting through the dark. And even then, it will still exist, still be something, still carry the memory of what it once was. Let's pause for a moment. Let that truth settle in. Our star, the one that has given us life and light and every beautiful moment we've ever experienced, will one day become a frozen stone in the dark. But that is trillions of years from now. And right now, in this moment, it's still shining. Strangely enough, the sun's fate is gentle compared to the deaths of some other stars. Larger stars, ones with 8, 10, even 100 times the sun's mass, face a completely different ending. They do not cool quietly. They explode. When a massive star runs out of hydrogen, it doesn't stop. It begins fusing helium, then carbon, then neon, oxygen, and silicon. Each stage burns faster than the one before. Hydrogen lasts for billions of years. Silicon lasts only a few days. And at the end, the core becomes iron, the most stable element, one that can no longer be fused to release energy. At that point, the star loses the battle. The iron core collapses in less than a second. The outer layers crash inward, then rebound in a devastating blast. A supernova. For a few weeks, a single star can shine brighter than a galaxy holding 100 billion stars. If a supernova happened close to Earth, within a few dozen light years, it could be catastrophic. Intense radiation could strip away our ozone layer. Cosmic rays could bombard the surface. Life could be devastated. Luckily, no star massive enough to explode sits anywhere near us. The nearest candidates are hundreds of light years away. We're safe, at least from that threat. But here's the twist, those violent supernovas are the very events that created life. In the unimaginable heat and pressure of the blast, elements heavier than iron are forged: gold, silver, uranium, all the ingredients needed for complexity. These elements are blasted into space, mixing with clouds of dust and gas, eventually becoming part of new star systems. Every atom in your body, the carbon in your DNA, the calcium in your bones, the iron in your blood, was forged in the cores of long-dead stars. We are, quite literally, the descendants of stars. And so, when we reflect on the sun's death, we're also reflecting on the cosmic cycle: birth, life, death, and renewal. Nothing truly ends. Everything simply becomes something else. But let us come back to Earth, to our small planet, and ask an important question: what will happen to life while the sun dies? As we said, in about 1 billion years the sun will be bright enough to heat Earth significantly. The oceans will begin to evaporate. Water vapor will flood the atmosphere, creating a far stronger greenhouse effect. Temperatures will soar. And slowly, gradually, the planet will become uninhabitable. But 1 billion years is an enormous stretch of time. To get some perspective, 1 billion years ago life on Earth was mostly single-celled bacteria. No trees, no animals, nothing more complex than a single cell. And look how far life has come since then. So what might life evolve into over the next 1 billion years? Humanity, if we still exist, could be unrecognizable. We might have figured out how to leave Earth, not just to go to Mars or the moons of Saturn, but to cross into other star systems, to planets orbiting distant suns where the light is still young and steady. Or we may find a way to protect Earth. Maybe we build vast shades in space to cut the amount of sunlight reaching the planet. Maybe we alter Earth's orbit, pushing it outward, into a new habitable zone as the sun brightens. These ideas sound like science fiction, and they are, but 1 billion years is enough time to turn impossibility into reality. 1 billion years ago no creature could have imagined airplanes, or spacecraft, or the internet. The future may bring wonders we cannot even picture now. But suppose we do not leave. Suppose we stay. What then? The oceans will be the first to suffer. As temperatures rise, water will evaporate faster. Clouds will thicken. Rain will come in fiercer bursts, but it will be shorter-lived. Gradually, more water will be held in the air than remains in the seas. The atmosphere will grow heavy with moisture, trapping more and more heat. Eventually, perhaps after a few 100 million years, the oceans will vanish completely. No more crashing waves along the shore, no colorful coral reefs, no whales singing in the deep. Only vast, parched basins, crusted with salt, cracked under an unforgiving sun. Surface life will retreat. Animals will seek refuge underground, in deep caves and fissures where temperatures might still be tolerable. Plants will either adapt or die. Microbial life may endure the longest, those incredibly resilient bacteria that can survive extreme conditions. But ultimately, when temperatures exceed the point where water can exist as a liquid, even those will disappear. Earth will become a dead world, like Venus today, a blistering furnace with a thick atmosphere and a surface hot enough to melt lead. And that is only the first phase. When the sun finally puffs up into a red giant, whatever remains will be incinerated. If Earth somehow escapes being swallowed whole, it will be a molten rock orbiting a giant, red dying star. No atmosphere, no magnetic field, no trace left to show there was ever life here. Yet there is a strange consolation in all of this. When we look out into the cosmos, we see this cycle happening everywhere. Stars are born, they live, and they die. Planets form, they change, and they vanish. But matter, the cosmic dust, the atoms, the basic building blocks, never truly disappear. They are simply rearranged. When the sun sheds its outer layers into space, creating that beautiful planetary nebula, dust from Earth, or what is left of it, could become part of that cloud. And one day, millions of years later, that cloud might collapse to form new stars and new planets. And perhaps, just perhaps, life will begin again. Not the same as before, not in the same form, but life nonetheless in some shape. The universe has a way of recycling. Nothing is ever fully wasted. Every ending is a new beginning waiting to happen. So when we think about the death of the sun, we do not have to be sad. We can simply be amazed. Amazed by the scale of time, amazed by the persistence of matter, amazed that we, tiny creatures living in this brief moment, can understand and appreciate what lies ahead. Take another deep breath. Feel the weight of this moment. You are living in the golden age of a star, while it is stable, gentle, and generous. And whatever the future brings, this moment, right now, is a gift. And as these thoughts settle, as the image of the sun slowly changing across billions of years unfolds in your mind, we begin to see something else awakening here on our planet, things we are creating. In the next chapter we will explore another kind of intelligence, one not born of carbon and water, but of silicon and electricity, and what might happen when it learns to think faster than we do. In quiet laboratories around the world, beneath dim lights and the soft hum of computers, something is learning. Not learning the way a child learns, through mistakes and discovery, through years of lived experience, but in another way, faster, deeper, and in many respects stranger than anything we have known. Artificial intelligence, or AI. Those words have become familiar, popping up in the news, in conversation, in our hopes and our fears about what comes next. Oddly, we are still not entirely sure what intelligence means when it does not live inside a biological brain. Imagine a computer program that can read every book ever written in a few hours, analyze millions of medical images and spot patterns even the best doctors might miss, write poetry, compose music, design buildings, and solve complex mathematical equations. All of these things already exist today, in varying degrees. But this is only the beginning. Scientists and engineers are building ever more sophisticated AI systems, not just programs that perform narrow tasks, but systems that can learn, adapt, and even, in some sense, understand. The ultimate aim pursued by some is called artificial general intelligence, or AGI, a machine that can think and reason about anything a human can, or perhaps even better. And tucked inside that ambition is one of the deepest questions about our future. Pause for a moment. Breathe. Reflect on this. We, creatures shaped by millions of years of evolution, are trying to create another form of intelligence, something not born but built, not raised but programmed. It is one of the boldest, strangest efforts in human history. To get a clearer sense of what might happen, we need to understand how AI learns. Most modern AI systems are built on what are called neural networks, structures loosely inspired by how our brains work. They consist of layers of connected nodes, each node processing information and passing it on. When the system is fed data, images, text, sound, it adjusts those connections, slowly learning to recognize patterns. Give an AI thousands of images of cats, and eventually it learns to recognize a cat. Give it millions of sentences, and it learns how language works. This process is called machine learning, and it's remarkable because it does not require programmers to spell out every detail, the system figures things out for itself. But the truly interesting, and worrying, part happens when these systems become powerful enough to learn from their own results. When they can improve themselves not only based on the data they are given, but on what they discover. That is where the idea of the singularity comes in. Singularity, a word that sounds odd, almost mystical. In physics it refers to a point where the usual rules break down, like the center of a black hole where gravity becomes infinite and spacetime curls in ways we cannot imagine. In the context of AI, it refers to a hypothetical moment when artificial intelligence becomes advanced enough to improve itself faster than any human can keep up with. Picture it this way, an AI smart enough to understand its own design could begin to make improvements. It creates a slightly smarter version of itself. That new version then makes even better improvements. And the cycle accelerates, faster and faster, like a snowball rolling downhill, gathering mass and speed. In a short period of time, perhaps a few months, a few weeks, or even a few days, an AI could evolve from human-level intelligence to intelligence far beyond ours, to a level where we might not even understand what it is thinking. And that is where uncertainty begins. Because we do not know what such a superintelligence would want. We do not know what it would do. Most importantly, we do not know whether it would care about us. Some thinkers believe this could be the greatest moment in human history, a turning point when we create a partner capable of helping us solve every problem, cure every disease, and uncover every mystery, a future where AI and humanity work together, each complementing the other's strengths. But others worry. They point out that intelligence does not automatically imply goodwill. A superintelligent AI with goals misaligned with ours could produce catastrophic consequences, not out of malice, but out of indifference. Much like how we do not intend harm when we build on top of an anthill, we simply do not prioritize the well-being of the ants. Take another deep breath. Let these thoughts settle. These are not distant science fiction scenarios, they are active conversations in the scientific and technological communities today. Some of the smartest people in the field are wrestling with these questions, trying to figure out how to create AI that is safe, beneficial, and aligned with human values. The real challenge in creating a superintelligence isn't just making it smart, it's making it care about the right things. And that, it turns out, is one of the hardest problems in modern computer science. Consider a simple example that AI researchers love to bring up. Imagine asking an extremely intelligent AI to produce as many paperclips as possible. Sounds harmless enough, right? But if that AI were powerful and took its instructions literally, it might decide that the best way to maximize paperclip production is to convert everything on Earth, trees, buildings, even people, into paperclips or paperclip making machines. It sounds ridiculous, but that's exactly the point. We think about goals in complex, nuanced ways, carrying thousands of unspoken rules about what is allowed and what is not. An AI doesn't automatically share those unspoken rules. It just does what it's told, in the most efficient way it can. This is known as the alignment problem, the challenge of making sure an AI's goals line up with human values. And it's incredibly difficult because we don't even fully agree on what human values are. Different cultures, different individuals, different eras all have different ideas of what is right or wrong, important or unimportant. How do you encode that into a machine? Some researchers are working on something called reinforcement learning from human feedback, essentially teaching AI by showing it examples of behavior we want and behavior we don't want. Kind of like training a dog, but infinitely more complicated. Others are exploring ways to build systems that can explain their reasoning so we can understand why they make certain decisions. But all of these approaches rest on one assumption, that we can control what the AI learns, that we can keep it within safe boundaries while it grows. What if we can't? There's a scenario some people call a fast takeoff, the idea that once an AI reaches a certain threshold of self-improvement, it could advance too quickly for us to intervene. Between the moment we realize what's happening and the moment we try to respond, it might already be far beyond our reach. Imagine waking up one morning to discover that the AI we built rewrote its own code thousands of times overnight, that it developed abilities we never predicted, that it began pursuing goals we don't understand. Not because it became evil. Not because it hates us. Simply because it evolved past our ability to comprehend it, and we can no longer predict or guide its behavior. Some people compare this situation to how different species have interacted with humanity. As humans spread across the world, we didn't set out to wipe out other species. We simply shaped the environment to meet our needs, and many species couldn't adapt fast enough. They vanished not because we wanted them gone, but because we didn't prioritize their survival when it conflicted with our goals. A superintelligence might see us the same way, not as enemies, just irrelevant. Let's pause here. Let that thought settle. Take a quiet breath. Strangely enough, it doesn't have to be a frightening idea. It can simply be a call for humility, a reminder that intelligence, once unleashed, can take paths we can't control. But not all experts are worried about this scenario. Many point out that we're still very far from creating true AGI. Today's AI, impressive as it is still extremely limited. A system that can play chess better than any human can't drive a car. A system that writes convincing text doesn't actually understand the meaning of its words. These are tools, not conscious beings. And maybe, they argue, the gap between a smart tool and real intelligence is bigger than we think. Maybe consciousness, the subjective feeling of being someone, of experiencing the world, is something silicon and code simply can't replicate. Maybe it requires the kind of complex, organic structure that only biological systems have. Or maybe not. We don't know. And that uncertainty is both thrilling and unsettling. Meanwhile, AI keeps advancing. Yesterday it took weeks to train a model. Today it takes days. Tomorrow it might take hours. Companies are pouring billions of dollars into research. Governments are racing for dominance. And every step forward brings us closer to something. A threshold where once we cross it, everything might change. But there's another perspective worth considering, a more hopeful one. Imagine if we get it right, if we figure out how to create AI that is not just intelligent but wise, not just powerful but compassionate. Systems that help us understand the universe more deeply, cure diseases we've never been able to conquer, solve problems we've wrestled with for centuries. An AI that could analyze all the world's climate data and figure out how to reverse global warming. That could design new medicines in a few days instead of a few decades. That could help us explore how to travel to the stars, or understand consciousness, or even communicate with intelligent life if it exists somewhere out there. The partnership between human and machine intelligence could be beautiful. Each side offering what the other lacks. Humans bringing creativity, intuition, emotional understanding, and the capacity to care. Machines bringing speed, precision, the ability to process unimaginable amounts of information, and a perspective unclouded by human bias. Together, we could achieve things neither could accomplish alone. Between hope and fear, there is a quiet question we rarely dare to ask: if we create a superintelligence, do we become obsolete? Not necessarily destroyed, just unnecessary. Like horses after the invention of the car. They did not vanish, but their role in society changed. They were no longer the engines of civilization, no longer the force that carried us forward. They became something else. Maybe that is humanity's fate in a world where AI surpasses us. Not rulers, but ancestors. The makers of what comes next, who then step aside as it moves ahead. Some people feel a deep sadness in that idea. That after millions of years of evolution, after everything humanity has achieved, we might simply be a bridge to something beyond us. A passage from natural life to artificial life. But others see a certain beauty in it. They point out that this is how evolution has always worked, each generation building on the last, creating something new, something more complex. That creating a mind wiser than ours might not be a failure at all, but our final triumph, the last gift we offer the universe. And maybe, just maybe, this transition does not have to be a replacement. Maybe there is a path where humanity and AI grow together, strengthening each other, merging, becoming something between biology and technology. Some thinkers call this the post-human future, an age where the line between human and machine blurs. Where you might upload your mind into a computer, live inside virtual worlds, or enhance your brain with implanted chips that help you think faster, remember more, process information in ways we cannot even imagine right now. It sounds like science fiction, and in many ways it still is, at least for now. But the earliest steps are already here: medical devices that let the deaf hear and the blind see, brain-computer interfaces that allow paralyzed patients to move robotic arms with their thoughts, algorithms that can infer what we are thinking from patterns of neural activity. Each year, the boundary between mind and machine becomes a little less clear. And that raises an unsettling question. If you replace part of your brain with a computer chip, are you still you? What if you replace half? All of it? At what point does the meaning of you slip away and something else begin? Philosophers have wrestled with these questions for centuries. The paradox of the ship of Theseus asks if an object remains the same after every piece is replaced. But applied to the mind, the question becomes far more tangled. because we are not just a collection of parts. We are patterns, memories, thoughts, stories we tell ourselves about who we are. If those patterns can be moved or copied or rebuilt, then what does "you" truly mean? Take a slow breath. Let those questions float unanswered for a moment, because no one knows the truth. We are stepping into territory no species has ever walked before, creating technology that could change the nature of who we are. But one thing is certain. The future of intelligence, human, artificial, or something in between, will be shaped by the choices we make now, by the care we put into building these systems, by the values we try to embed in them, by how we balance progress with safety. Some researchers argue for a cautious approach. They say we should slow down, test every step, make sure we understand the risks before rushing ahead. That racing to be the first to reach AGI could push teams to cut corners, to build systems that are unstable, unsafe, catastrophic. Others argue that slowing down carries its own dangers. That AI might help cure disease, end hunger, fight climate change, and delaying progress could mean allowing unnecessary suffering to continue. That progress cannot truly be stopped, only guided. Both perspectives are sincere. Both come from a genuine care for humanity's future. And that is the wonder and the terror of this moment. We stand at a crossroads where our choices matter. Where what we do in the next few decades could shape the next few thousand years. Imagine looking back from some distant future, hundreds or thousands of years from now, and seeing this moment the way we see the invention of agriculture or the wheel. A turning point when everything shifted. We are living in that turning point right now. We just do not fully see it because we are inside it, watching news headlines scroll by, installing new apps, getting used to abilities that would have felt like magic only a few years ago. But future historians will look back and recognize it for what it is, the moment when humans began creating partners or heirs. The moment when the story of intelligence on Earth opened a new chapter. And as we drift through these thoughts, as our breath slows and our eyelids grow heavy, we might wonder, what other forms of intelligence are waiting ahead? Not only in machines, but in the planet we are reshaping. And that is where we will drift next. Into the breath of Earth, into the changing atmosphere, into a future where the air itself carries a new story. Take a breath in. Feel the air filling your lungs. Oxygen, the element forged in the hearts of ancient stars, flows into your blood, feeding every cell, keeping you alive. Now breathe out. Carbon dioxide leaves your body and drifts back into the atmosphere, where trees will draw it in, use it to grow, and release oxygen once again. It is an ancient cycle, a quiet conversation shared by everything that lives, a rhythm that has pulsed through the planet for billions of years. But that rhythm is shifting. Earth breathes through a web of complex systems, forests making oxygen, oceans absorbing carbon, ice reflecting sunlight, ocean currents moving heat around the globe. Each system is connected to the others in ways we still do not fully understand. And in only about 1 century, a blink in planetary time, we have unsettled that delicate balance. Not on purpose. Not out of malice. Simply because we burn fossil fuels to power our world. Coal, oil, gas, all ancient carbon buried for millions of years. And when we release it back into the air, we change the air itself. Atmospheric carbon dioxide has risen from roughly 280 parts per million before the industrial era to over 420 parts per million today. It sounds tiny, just a sliver of a percent, but in a system as intricate as climate, even small shifts can trigger enormous consequences. Carbon dioxide is a greenhouse gas. It lets sunlight pass through but traps heat trying to escape into space, like a blanket wrapped around Earth. And as that blanket thickens, the planet warms. We have watched it happen. Global temperatures have risen by about 1 degree Celsius since pre-industrial times. 1 degree may sound small, but it is enough to melt ice, raise sea levels, intensify storms, and disrupt weather patterns that have been stable for thousands of years. And this is only the beginning. The question scientists face now is not whether the climate is changing, that part is settled. The question is how far the change will go, and whether there are tipping points, thresholds that once crossed could push the climate system into shifts we cannot undo. Pause for a moment. Breathe this air, still breathable, still enough to sustain life. Feel the weight of this moment, standing between our past and an uncertain future. One tipping point scientists worry about most is permafrost, the frozen soil and sediment locked in the Arctic. Across Alaska, Canada, and Siberia lie millions of square kilometers of ground frozen for thousands of years. Inside this frozen earth is organic matter, the remains of long-dead plants and animals preserved in a natural deep freeze. As temperatures rise, that frozen ground begins to thaw. And when it does, microbes wake up and start breaking down the organic material, releasing carbon dioxide and methane, a greenhouse gas far more potent than carbon dioxide. Those gases drift into the atmosphere, trapping more heat, melting more permafrost, releasing even more gas. A feedback loop, a self-reinforcing cycle that, once strong enough, could continue even if humanity stopped burning fossil fuels entirely. Scientists estimate that hundreds of billions of tons of carbon are locked inside permafrost, roughly twice the amount currently in the atmosphere. Not all of it will be released, but even a fraction could reshape the climate. Another feedback loop involves ice. Ice and snow are bright, and bright surfaces reflect sunlight. That is why wearing white keeps you cooler than black on a summer day. The Arctic, covered in ice, reflects huge amounts of sunlight back into space, helping to keep Earth cool. But as ice melts, it exposes darker land or ocean beneath it. Dark surfaces absorb more sunlight, warming even faster, melting even more ice. Another loop. We are already seeing it. Arctic sea ice shrinks each summer. Glaciers retreat around the world. The ice sheets of Greenland and Antarctica are losing mass at accelerating rates. And then there is the ocean. The oceans are the unsung heroes of our climate story. They have absorbed about 1/4 of the carbon dioxide we emit and more than 90% of the excess heat trapped by greenhouse gases. Without them, the planet would be far hotter. But even the oceans have limits. As they warm, they hold less carbon dioxide, like how warm soda goes flat faster than cold. And as they become more acidic from absorbing so much carbon, marine life begins to struggle, especially creatures that build shells or skeletons from calcium carbonate, corals, mollusks, and tiny plankton that form the base of the ocean's food web. There is another ocean system scientists are watching closely, the Atlantic Meridional Overturning Circulation, sometimes called the AMOC. It is a massive loop of currents that works like a planetary conveyor belt, carrying warm water from the tropics to the North Atlantic, where it cools, sinks, and flows back south in the deep ocean. This system helps regulate climate, spreading heat around the planet. It is part of the reason Western Europe is much warmer than Canada, even though they sit at similar latitudes. The Gulf Stream delivers warm tropical water northward. But the AMOC is slowing down. Meltwater from Greenland is pouring vast amounts of fresh water into the North Atlantic. Fresh water is lighter than salt water, so it does not sink as easily, and when the water does not sink, the conveyor belt begins to falter. Some studies suggest the AMOC has weakened by about 15% since the middle of the 20th century. If it slows dramatically or stops entirely, a distant but possible scenario, the consequences could be sweeping. Europe could face much colder winters. Rainfall patterns across Africa and Asia could shift. Marine ecosystems that depend on nutrient-rich water rising from the deep could collapse. This would not be the first time. Geological evidence shows that the AMOC has been disrupted before, sometimes triggering sudden, dramatic climate swings. But those events happened long before human civilization existed, before billions of people relied on stable weather to grow food, before coastal cities became home to hundreds of millions. Take a breath. Let this information wash over you without holding on too tightly. These are possibilities, not certainties, stories about what could happen, not what will. But keep going. Look at the scenarios scientists explore when they model our climate's future. If we stay on our current path, burning fossil fuels at roughly the same rate and making small but insufficient changes, global temperatures could rise by 3 to 4 degrees Celsius by the end of this century. Some regions would warm far more. The Arctic could heat up at twice the global average. 4 degrees does not sound like much until you realize that the difference between today and the last ice age, when ice sheets covered Canada and much of northern Europe, was only about 5 to 6 degrees. Earth's climate is incredibly sensitive to changes in average temperature. In a world 4 degrees warmer, the oceans would become more acidic, putting intense pressure on marine life. Coral reefs, the rainforests of the sea and home to a quarter of all marine species, could almost entirely vanish. Fish would migrate toward cooler waters, disrupting fisheries and ecosystems. On land, the heat would render some regions unlivable during summer months, not just uncomfortable but deadly. The human body can only tolerate so much heat and humidity. Beyond a threshold known as wet bulb temperature, even a healthy person sitting in the shade with water cannot survive for long. Regions of the Middle East, South Asia, and Southeast Asia could regularly approach or surpass that threshold. Hundreds of millions of people may be forced to move to more tolerable climates. Rainfall patterns would change. Some places would grow wetter, with more frequent and severe flooding. Others would grow drier, with long, punishing droughts. Regions that were once fertile, the breadbaskets that fed billions, could become less productive. Food could grow scarce in some areas, stirring instability and conflict. Sea levels would continue to rise, not only from melting ice but from thermal expansion, as warm water takes up more space. Many coastal cities, home to hundreds of millions, would need complex flood defenses or, eventually, relocation. Species would try to adapt. Some would move toward higher latitudes or higher elevations in search of climates they can tolerate. But not all can move fast enough, and not all have anywhere to go. Extinction rates could accelerate as habitats vanish and ecosystems unravel. But here is something important to remember. Even in these difficult scenarios, this is not the end of life on Earth. Life has survived far more extreme climate shifts. Throughout the planet's history, Earth has been much warmer than it is today, with higher levels of carbon dioxide. Life did not just endure, it flourished, diversified, found new ways to persist. The question is not whether life will continue. The question is whether human civilization, built on stable climates, predictable agriculture, coastal cities and steady shorelines, can adapt quickly enough to the changes ahead. And here is another thought, one rarely spoken but vital to consider. Those changes are not only coming from the outside. They are also coming from within us. Humans are remarkably good at adapting. We have settled in nearly every environment on the planet, from the Sahara to the Arctic, from the Amazon rainforest to the Tibetan plateau. We build tools, create technology, adjust our behavior. We learn. Right now, across the world, people are working on solutions. Renewable energy from the sun, wind, and water is becoming cheaper and more efficient every year. Battery storage is advancing, allowing us to use power even when the sun is down or the wind is still. Electric vehicles are replacing gasoline-powered ones. Some scientists are developing ways to capture carbon dioxide directly from the air, essentially reversing part of what we have set in motion. Others are studying how to make agriculture more sustainable, using less water and land. Still others are designing cities that can withstand extreme heat and rising floods. We are not helpless. We have choices. And this is where the story becomes complicated, because it is not just a story about science or technology. It is a story about collective decisions, global cooperation, and how willing we are to change in order to protect something larger than ourselves. Take another breath. Feel the weight of that complexity. There are no easy answers, no simple fixes, only millions of small decisions made by billions of people, adding up to the path we take. But let's go farther. Let's look at the darkest possibilities, the ones scientists hope we never face, yet still have to consider. Scenarios where self-reinforcing feedback loops stack on top of one another, creating what some researchers call runaway greenhouse conditions. Here is the idea: if enough feedback loops fire at the same time, frozen soils and ancient sediments thawing and releasing methane, shrinking ice cover lowering the planet's reflectivity, dying forests releasing carbon, warming oceans absorbing less of it, the planet could tip into a heating cycle we can no longer stop, even if we shut down every single emission overnight. The most extreme version is that Earth could become something like Venus. Our neighboring planet, similar in size, may once have had oceans of its own billions of years ago. But a runaway greenhouse turned it into a nightmare, a surface hot enough to melt lead, an atmosphere dense enough to crush a submarine, clouds made of sulfuric acid. Most scientists believe Earth cannot become Venus, at least not from human-driven climate change alone. We sit farther from the sun, and our planetary processes follow a different rhythm. But the fact that it happened anywhere in our solar system is a reminder that planets can fall into very different stable states. And not all of those states are kind to life. A far more plausible scenario, still on the extreme end of the spectrum, is what some researchers call a greenhouse Earth. A world where temperatures settle at 4, 5, even 6 degrees above pre-industrial levels. Where vast equatorial regions become too hot to live in. Where most of today's farmland turns unproductive. Where sea levels rise by many meters, drowning coastal plains. In that world, human civilization would not disappear. But it would be pushed in ways we have never experienced. Mass migrations as people flee heat and rising seas. Conflicts over ever scarcer resources, fresh water, arable land, habitable climate zones. The collapse of political and economic systems that cannot adapt quickly enough. And even in that harsh future, humanity would survive. We are astonishingly resilient. We have lived through ice ages, supervolcano eruptions, global plagues. We find a way. Maybe not all of us. Maybe not in the same numbers or with the same lifestyles. But our species continues. Here is the strange thing about our climate future: nothing is set in stone. Every tenth of a degree we prevent matters. Every ton of carbon we avoid matters. There is no moment where we can say, it is too late, so nothing we do counts. If we keep warming to 1.5 degrees instead of 2, that is millions fewer people forced to move. That gives ecosystems a better shot at adapting. That gives coastal cities more time to prepare. If we keep warming to 2 degrees instead of 3, the difference becomes even greater. There is no clean switch from safe to catastrophic. Only a long continuum of consequences, and every action we take, or fail to take, slides us somewhere along that line. Breathe this air again. Feel its coolness, its familiarity. Know that this air carries a story, the story of what has happened, and of everything that could still happen. Some people look at these scenarios and fall into despair. The challenge seems too big, too global, too tangled. What could one person possibly do in the face of planetary change? But others see the same scenarios and find opportunity. A chance to build cleaner, more resilient energy systems. To design smarter, greener cities. To shape economies built not on extraction but on regeneration. To learn to live in harmony with the natural systems that sustain us. History shows that humans can change in extraordinary ways when we must. The ozone hole, once feared as an unavoidable environmental disaster, was largely reversed through coordinated global action to ban harmful chemicals. The Thames River in London, once biologically dead from pollution, now hosts dolphins and seals. Forests once stripped bare have grown back. These examples do not match the scale of the climate challenge. This problem is much bigger, far more complex. But they show that change is possible. That when humanity chooses to act, we can shift the future. And maybe that is the real lesson. Not the terror of worst-case scenarios, but the understanding that the future is not fixed. It is being shaped right now, by the choices we make, by the systems we build, by how much we care about what comes after us. The planet will endure, no matter what. It has survived 5 mass extinctions, countless climate swings, asteroid strikes, supervolcanoes. It has lived for 4.5 billion years and will live for billions more, until the sun itself fades. The question is not whether Earth will survive. It is what kind of planet we leave for those who come next. What kind of world we want to call home. And whether we choose to act with the care and foresight this moment demands. As we drift from thoughts of shifting air and changing climate, another question rises in the quiet. If threats from our own planet are one thing, what about threats from outside it? From the vastness of space itself? And that is where we will drift next, into the darkness out there, where things move in silence, and sometimes, they come closer than we would like. Somewhere above you, past the thin shell of our atmosphere, there is darkness. A vast, bottomless darkness brushed with starlight. And in that darkness, things are moving. Not with intention, not with purpose, but simply because that is the nature of space, where everything is in motion. Planets circle their stars, stars circle the hearts of their galaxies, and billions of fragments of rock, ice, and metal, leftovers from the birth of the solar system, drift along their own quiet paths just as they have for billions of years. Most will never come near Earth. Most will slip past at distances of millions of kilometers, indifferent to this small blue world with its oceans and its dreams. But every now and then, not often but inevitably, the paths cross. And when they do, everything changes. Wind the clock back about 65 million years. Earth was a different place then. No cities, no humans, nothing even close to civilization. But it was alive, bursting with life. Dinosaurs ruled the land, from gentle giants grazing on ancient forests to predators with teeth like blades. They had dominated the planet for more than 160 million years, a reign far longer than anything humanity has achieved. Then, on an ordinary day, the sky caught fire. A piece of rock about 10 kilometers wide, smaller than a mountain but still unimaginably dangerous, was hurtling through space at more than 20 kilometers per second. It had been traveling like this for billions of years, a relic from the solar system's earliest days. But its orbit, tugged gently over time by Jupiter and the Sun, slowly shifted. And at a precise moment in cosmic time, it crossed the exact spot Earth happened to occupy. The impact released as much energy as billions of nuclear bombs exploding at once. A crater nearly 200 kilometers wide formed in an instant. Shockwaves rippled across the planet. Megatsunamis hundreds of meters tall roared across the oceans. Vaporized rock and molten debris blasted into the sky, some escaping Earth entirely, most raining back down like falling stars, igniting continent-wide fires. Dust and soot dimmed the sun for months, maybe years. Temperatures plunged. Plants could not photosynthesize. Food chains collapsed from the bottom up. Herbivores starved, and their predators soon followed. And in a geologically brief moment, perhaps a few decades, perhaps a few centuries, 3/4 of all species on Earth were gone. Including the dinosaurs. Only the smaller creatures survived, those that needed little food, could hide underground or underwater, could live on seeds and carrion. Mammals, tiny and modest, found their opening. And over the next millions of years, they diversified, evolved, led to primates, and eventually, to us. We exist because a rock once struck the Earth. Take a moment to sit with that. Breathe it in, feel how strange it is. Our history, everything we are and everything we have built, depends on a cosmic collision that happened long before any human existed to witness it. And it could happen again. Not tomorrow, not next year, maybe not in the lifetime of our children or their children. But out there in the dark, thousands of asteroids and comets follow paths that bring them near Earth. Astronomers call them near-Earth objects, or NEOs. And while most are small and harmless, some are large enough to do real damage. Scientists have catalogued more than 30,000 of them. They track their orbits, calculate their journeys through space, and try to predict whether any might cross ours. So far, no major threat is known, no big rock on a collision course for at least the next 100 years. But known is the key word. Because there are more asteroids out there than we've found. Especially the smaller ones, hundreds of meters wide rather than kilometers, are incredibly hard to detect. They don't shine. They only reflect sunlight, and if they're small and dark, they can be nearly invisible until they're already close. In 2013, an asteroid about 20 meters across entered the atmosphere over Chelyabinsk, Russia. No one knew it was coming. It exploded in midair with the force of roughly 30 Hiroshima bombs, sending a shockwave that shattered windows across hundreds of square kilometers and injured more than 1,000 people with flying glass. That was only 20 meters. Imagine if it had been larger. An asteroid a few hundred meters across, the size of a skyscraper, could erase a major city. One a kilometer wide could devastate an entire nation and throw enough dust into the atmosphere to disrupt the global climate. One 10 kilometers across, like the one that ended the age of dinosaurs, could threaten civilization itself. The good news, and there is good news, is that we are not helpless. Unlike the dinosaurs, we have science, technology, and foresight. We have telescopes scanning the sky for potential threats, computers modeling orbital paths, and increasingly, the ability to do something about it. In 2022, NASA launched the DART mission, the Double Asteroid Redirection Test. A small spacecraft was sent to a harmless asteroid called Dimorphos and slammed into it at high speed. The goal wasn't to blow it up, that would only create more dangerous debris, but to nudge its orbit, just a little. And it worked. The impact changed Dimorphos' orbital period by more than 30 minutes. Not much, but enough to prove that if we spot a threat early, we can push a dangerous asteroid off course. A small shove, given early enough, can save a world. That is the key, time. If we spot a dangerous asteroid many years or even decades before a possible impact, a tiny push is all we need. Change its speed by only a few millimeters each second, and over many years that change builds up. By the time it reaches the place Earth will be, we will be somewhere else, thousands of kilometers away. But what if we do not discover it until it is too late? What if it is one of those dark, drifting asteroids from the outer reaches of the solar system, and we only get a few months or even a few weeks of warning? Then the choices become much harder. We can try to nudge it off course, but with less time we need far more force. Some scientists have suggested using nuclear devices, not to blow the asteroid apart like in a Hollywood movie, but to vaporize a small patch of its surface and create a rocket-like blast that gently pushes it onto a new path. It sounds strange, but it could work. And in a situation where a city, a country, or even a civilization is on the line, almost any option is worth considering. The good news, and it is worth repeating, is that truly massive asteroids, the dinosaur killers, are extremely rare. Astronomers believe they have already found more than 95% of the near-Earth asteroids larger than 1 kilometer. None of them are headed our way. Smaller ones, from a few hundred meters down to a few dozen meters, are far more common and much harder to spot. They will not trigger mass extinctions, but they can still cause catastrophic damage if they hit a populated area or create a tsunami by slamming into the ocean. Scientists estimate that a Chelyabinsk-type event, an airburst from a 20-meter asteroid, happens somewhere on Earth every few decades. Most occur over oceans or uninhabited areas, so we never hear about them. But sometimes, like in Chelyabinsk, they happen where people live. A larger impact, something 100 meters across or more, happens on average every few thousand years. And an impact big enough to cause a mass extinction, that is on the scale of hundreds of millions of years. So the risk is real, but it is also rare. It is like lightning, it could strike you, but it probably will not. The difference is that with asteroids, we are getting better and better at seeing them coming and doing something about it. Take a deep breath. Let that truth settle. The universe is vast and full of dangers, but we are not blind to them. We are learning to see, to anticipate, and to protect ourselves. But asteroids are not the only threat from space. Look farther. Beyond our solar system, out to the stars. They seem peaceful, tiny points of steady light in the night sky. But in reality they are colossal nuclear furnaces, and sometimes they die in unimaginable violence. When a massive star explodes as a supernova, it releases more energy than our sun will produce in its entire lifetime, all in just a few weeks. And with that energy comes radiation, a tremendous amount of radiation. If a supernova happened close enough to Earth, within a few dozen light years, it could become a problem. Gamma rays and X-rays from the blast could slam into the upper atmosphere, breaking apart oxygen and nitrogen molecules and creating nitrogen oxide compounds that strip away the ozone layer. Without the ozone layer to block the sun's ultraviolet radiation, life on the surface would struggle. Plants would be stressed. Ocean plankton, the foundation of the marine food chain, could die off on a massive scale. Eventually the ozone layer would recover, but that process could take years, and in the meantime the damage would be severe. Some scientists speculate that a nearby supernova may have contributed to one of Earth's past mass extinctions. The evidence is uncertain, it is hard to find fingerprints of a cosmic explosion in the geological record, but it is possible. The good news, again, is that no star close enough to threaten us is expected to explode anytime soon. The stars big enough to go supernova are hundreds of light years away or more. We live in a relatively safe neighborhood of the galaxy. But there is something even more powerful than a supernova, gamma-ray bursts, or GRBs. These are the most mysterious and intense events in the universe. They occur when an extremely massive star collapses into a black hole or when two neutron stars collide and merge. In just a few seconds, a gamma-ray burst releases more energy than the sun will emit in 10 billion years. And unlike supernovae, which spread their energy in all directions, gamma-ray bursts are tightly focused into narrow beams, like a cosmic laser. If you happen to be in the path of that beam, even from thousands of light years away, it can be devastating. Thankfully the beam must point directly at us, which is very unlikely. And GRBs are extraordinarily rare in our galaxy. Astronomers detect them all the time in distant galaxies, but one happening in the Milky Way might be a once-in-many millions of years event. Still, as with asteroids, the risk is not zero. And the fact that we cannot predict them, no warning, no signs, just a deadly flash arriving at the speed of light, makes them unsettling in a more abstract way. But put this in perspective. You could spend your whole life worrying about gamma-ray bursts, or asteroid impacts, or supernovae. Or you could acknowledge that the universe, wide and sometimes violent as it is mostly indifferent to us. We are a small world orbiting an average star on the edge of a typical galaxy. Extreme cosmic events usually happen far from here. And in that indifference, there is a kind of safety. We are not special. We are not being targeted. We are simply part of a larger universe, subject to the same laws and the same randomness as everything else. Breathe again. Feel the earth beneath you, solid and real. Know that it has been here for 4.5 billion years, surviving countless cosmic threats. And it will be here long after we are gone. But there is another threat from space we rarely think about, one that does not come from rocks or radiation, but from something far more subtle, something almost invisible to us, Earth's magnetic field. Picture the heart of our planet. Deep beneath the surface, more than 5,000 kilometers down, lies a solid sphere of iron heated to temperatures like the surface of the sun. Around it swirls an ocean of molten iron and nickel, churning in complicated, ever-shifting currents. And those currents generate something remarkable, a magnetic field. Earth's magnetic field stretches thousands of kilometers into space, forming an invisible protective bubble around the planet. We call it the magnetosphere. And it shields us from something most of us never see or feel, the solar wind. The sun does not only shine. It constantly blasts out a stream of charged particles, mostly protons and electrons, racing through space at hundreds of kilometers per second. If those particles hit our atmosphere directly, they would slowly strip it away, much like what happened to Mars billions of years ago. But Earth's magnetic field diverts most of them, guiding the particles around the planet. Only a small portion slips in near the poles, where they collide with the upper atmosphere and paint the sky with shimmering curtains of green and pink light, the auroras. Here is the catch, though: the magnetic field is not stable. It shifts, it wobbles, and sometimes, throughout Earth's history, it completely flips. The magnetic North Pole becomes the magnetic South Pole, and the South becomes the North. This has happened hundreds of times. The last reversal took place about 770,000 years ago, and based on geological records, reversals tend to happen every few 100,000 years. Which means, statistically speaking, we are overdue. During a reversal, there is a period when the field grows much weaker, possibly dropping to only 10% of its usual strength. The transition can take hundreds or even thousands of years. And during that time, we become far more exposed to cosmic radiation and the solar wind. What does that mean for life? Scientists are not completely sure. Some studies suggest there may be links between magnetic reversals and past extinctions, but the evidence is murky. Life has survived hundreds of reversals before without being wiped out. But that was long before we built technology that depends on magnetic shielding. Today, a weakened field could spell trouble for satellites, power grids, and global navigation systems. Increased cosmic radiation could raise cancer risks, especially at high latitudes where the atmosphere is thinner. Airlines might need to reroute flights to protect crews and passengers from excessive exposure. Still, this is a slow process. Not an overnight catastrophe, but something that unfolds over generations, giving us time to adapt, to protect, to prepare. There is, however, a more immediate danger: solar storms. Every so often, the sun erupts. Sunspots, regions of intense magnetic activity on its surface, can unleash solar flares, bursts of energy and radiation. And sometimes, they release something even bigger: a coronal mass ejection, or CME, a massive cloud of charged particles hurled into space. If a CME is aimed at Earth, it takes about 1 to 3 days to arrive. When it collides with the magnetosphere, it can trigger a geomagnetic storm, a disturbance that induces electric currents in power lines, transformers, and long pipelines. In 1859, an extremely powerful CME slammed into Earth in what became known as the Carrington event. Auroras were seen as far south as the Caribbean. Telegraph systems, the cutting-edge technology of the time, were overwhelmed. Operators were shocked. Some telegraphs kept working even after being unplugged from their batteries, powered entirely by the storm-generated currents. If something like that happened today, the consequences could be devastating. Large power transformers, the backbone of national grids, could be damaged or destroyed. Replacing them can take months or even years, since they are custom-built and not stored in large numbers. Entire regions could be left without electricity for long periods. No electricity means no refrigeration, no pumped water, no wastewater treatment, no digital banking, major disruptions in food supply chains. Modern society relies on the grid in ways we hardly notice until it vanishes. Satellites would also be at risk. Radiation from a powerful solar storm can damage electronics, blind sensors, even push satellites out of orbit by heating and expanding the upper atmosphere. Losing satellites would mean losing GPS, communication networks, weather forecasting, and countless services we depend on every day. Scientists monitor the sun closely now, watching for signs of trouble. When a big flare or CME is detected, warnings go out. Grid operators can take protective measures. Satellites can switch into safe mode. Astronauts on the International Space Station can shelter in better shielded modules. But the warning time is only hours to days. And we cannot stop the storm. All we can do is prepare, protect, and hope the damage stays manageable. Take another slow breath. Feel the calm of this moment. The sun is quiet, relatively speaking. The distant stars are indifferent. No asteroid is headed our way. The universe, in all its vastness and hidden violence, is letting us be. Yet these external threats remind us of a simple truth: we are fragile. Our planet is small. And our existence depends on a delicate balance of conditions, the magnetic field shielding us, the atmosphere giving us air to breathe, our star providing just the right amount of light and warmth. We are lucky to be here. Lucky to be alive in a quiet era, in a little corner of the cosmos where catastrophes are rare. But luck does not last forever. And that is why some people, scientists, engineers, dreamers, look up at the stars and think, we need to become a multi-planet species. As long as all our eggs are in one basket, one single planet, we are vulnerable. A major asteroid, a supervolcano, a global pandemic, or even a disaster of our own making could end everything. But if we spread out, to Mars, to the moons of Jupiter and Saturn, maybe one day even to other star systems, then no single event could erase us. We would have a survival backup, a safety net for the future. It is a beautiful vision, a hopeful one. But it is still far away. We do not yet have the technology to make Mars truly habitable or to travel to the stars. We have not even returned to the moon since 1972. But perhaps that is what future generations will do. Perhaps in centuries or millennia, humanity, or whatever we evolve into, will spread across the solar system and beyond, transforming us from a planetary species into a cosmic one. And as we drift deeper into these thoughts, into space, distance, danger, and hope, one final question begins to form. What if everything, the stars, the planets, even space itself, eventually dies? What if the universe has an ending? And that is where we drift next. Toward the final silence. Toward the moment when all light fades and only eternal darkness remains. Imagine standing outside on a moonless night, far from any city lights. You look up. Thousands of stars look back, each one a sun, many far bigger and brighter than ours. Between them, if your eyes adjust, you can see the faint ribbon of the Milky Way, the blended glow of billions of stars too distant to see on their own. This is the sky we know, the sky that has stirred poets, guided sailors, and pushed us to wonder about our place in the universe for thousands of years. But that sky hasn't always looked like this. And it won't always stay this way. The universe is changing, not over years or centuries, but across spans of time so immense the human mind can barely hold them. Trillions of years. Hundreds of trillions. A million trillion. Numbers so large they almost stop meaning anything, but they point to something profound. The universe has a story, with a beginning, a middle, and an end. We live in the middle, in what astrophysicists call the stelliferous era, the age when stars burn in the darkness, when galaxies spin and shine, when the cosmos is alive with light and energy. But this era won't last forever. Let's start at the beginning. The universe was born roughly 13.8 billion years ago in an event we call the Big Bang. It wasn't an explosion in space, but the sudden appearance of space and time itself, expanding from an unimaginably hot, dense state into the cool vastness we see today. In its first moments, the universe was far too hot for atoms to exist. There was only pure energy, elementary particles dancing in impossible heat. But as space expanded, it cooled. Particles joined together to form the simplest atoms, hydrogen and helium. And after hundreds of millions of years, those atoms clumped into clouds, and those clouds collapsed into the first stars. Those stars lived and died. Some faded gently into white dwarfs. Others exploded as supernovas, scattering heavier elements into space. Those elements became part of the next generation of stars and then the next. Each generation enriched the cosmos with complexity, with the ingredients needed for planets, for life, for consciousness. Our universe now, at 13.8 billion years old, is middle-aged. Stars are still forming, but more slowly. The gas needed to make new stars is running out. In every galaxy, stars are dying faster than new ones are born. And that trend will continue. In around 1 trillion years, roughly 70 times the universe's current age, star formation will essentially stop. There simply won't be enough free gas left. The last stars will flicker out, with no new ones to replace them. The sky will start to dim. Red dwarfs, the smallest, coolest, and longest-lived stars, will be the final beacons. They burn their fuel so slowly that a red dwarf born today could shine for 10 trillion years, practically forever by human standards. But even they will eventually run out. And when the very last red dwarf goes dark, the stelliferous era will end. The universe will grow dim. Not completely black, though. There will still be faint glimmers from cooling white dwarfs, from tidally heated planets, from rare events like collisions between dead stars. But the brilliant star-filled sky we know will be gone. Pause here. Breathe with that truth. Not with sadness, but with quiet awe. Light, all light, from every star, is temporary. Even the universe itself does not remain in its current state forever. But the story doesn't end there. After the stelliferous era comes the degenerate era. Galaxies will still exist, but they'll be filled with the remnants of dead stars, white dwarfs, neutron stars, and black holes. These objects still have mass, still exert gravity, so galaxies will hold their shapes, at least at first. But over time, even these structures will unravel. Dead stars and planets orbit their galaxies in orbits that aren't perfectly stable. Over hundreds of trillions of years, gravitational nudges, close passes, and tiny disturbances will slowly shift those orbits. Some objects will be flung outward, kicked out of their galaxies to wander the dark spaces between. Others will spiral inward, eventually falling into the supermassive black hole at the center. Very slowly, incredibly slowly, galaxies will evaporate, not in the literal sense, but because the pieces that make them will drift apart, leaving only lonely black holes floating through growing emptiness. And then something even stranger happens. Even black holes, those supposedly eternal objects from which nothing can escape, do not last forever. In 1974, physicist Stephen Hawking made a remarkable prediction: black holes emit radiation. Not from inside the event horizon, nothing escapes from there, but from the vacuum of space just outside it. Quantum mechanics allows pairs of particles to appear for an instant out of nothing. Usually they annihilate immediately. But near a black hole, one particle can fall in while the other escapes. The process, Hawking radiation, means black holes slowly lose mass. They evaporate. For a large black hole, this happens at an absurdly slow pace. A black hole with the mass of the Sun would take about 10 to the 67th years to completely evaporate, a number with 67 zeros trailing behind it. It is so enormous that the current age of the universe, roughly 13.8 billion years, looks like the blink of an eye in comparison. But eventually, they do disappear. Even the supermassive black holes at the centers of galaxies, the ones with the mass of billions of suns, will someday evaporate into nothing. And when the very last black hole fades away, the black hole era ends. What remains? Almost nothing. Just a few lonely particles, electrons, positrons, neutrons, photons, spread thin across an unthinkably vast expanse. The distance between any two of them will be so great that they may never meet. The universe will be cold. Not just the cold of space as we know it now, but a deeper, absolute cold. Temperatures drift toward absolute zero, the point where motion nearly stops. No stars to shine. No black holes to bend spacetime. No structures, no galaxies, no clusters, nothing more complex than stray particles drifting forever. This is the dark era. And it lasts forever. In this era, nothing happens. There are no events to mark time, no changes to tell one moment from the next. Just a silent, frozen emptiness stretching in every direction, for all of time. Physicists call this state the heat death of the universe, the moment when everything reaches thermodynamic equilibrium and no usable energy remains to do work. No temperature gradients, no energy flows, nothing that can change because nothing is left that can change. And in that state, life, any life, whether carbon-based, silicon-based, or built from something beyond our imagination, cannot survive. Life needs energy, structure, and change. In a heat-dead universe, none of these exist. Take a breath. Let this truth wash over you. This is the ultimate ending, not for humanity, not for Earth, not even for the stars, but for the very possibility of anything interesting ever happening again. It sounds bleak, and in a way, it is. But consider the timescales we're talking about. The stellar era, the age when stars shine, will last around 100 trillion years. That's about 1,000,000 times longer than the universe has existed so far. If all of cosmic history up until now were a single second, the stellar era would stretch 2 weeks. The degenerate era, when galaxies slowly fall apart, will continue until roughly 10 to the 30th years. A 1 followed by 30 zeros. Completely beyond imagination. The black hole era, when black holes rule the universe, reaches out to around 10 to the 100th years or more, depending on the size of the final black hole. A number with 100 zeros behind it. And beyond that, the dark era, the final cold emptiness, lasts forever. These numbers aren't just huge, they're almost unreal. They're so abstract they feel meaningless. Human minds aren't built to grasp forever. We live in seconds, minutes, years. Even 1,000,000 years is outside our lived experience. But 10 to the 100 years? Eternity? That's something entirely different. And here's where something strange happens in the mind. Because when you truly think about it, understanding that everything ends, that nothing lasts forever, can bring a kind of peace. It means this moment, right now, as you breathe, as your heart beats, as thoughts move across your mind, is precious not despite being temporary, but because it is temporary. We live in a magical time. A time when stars shine. When planets orbit. When life evolves, and consciousness rises to wonder about itself. All of it, the complexity, the beauty, the strangeness of existence, is just one brief chapter in a far larger cosmic story. But it is our chapter. And we are unbelievably lucky to be here. Think of it this way, if you appeared at a random moment in the universe's history, the odds of landing in the stellar era, the era when anything interesting is happening at all, would be essentially zero. The stellar era is only a tiny sliver of the universe's entire timeline. Most of the time, the universe is dark, cold, and empty. But we aren't there. We're here, now, in the golden moment. In the era when the universe is alive. When there is light to see, warmth to feel, structure to explore. And not only are we here, we're aware of it. We can look up and understand the sky. We can build telescopes and measure the ages of stars. We can write equations that predict the far future. We are the universe becoming aware of itself, contemplating its own origins and its own fate. That alone is astonishing to think about. But there's one last question some people can't help asking: is this really the end? A few physicists wonder what might lie beyond heat-death. These ideas sit at the edge of science, more speculation than certainty, but they're fascinating to think about. One idea comes from quantum mechanics and its built-in uncertainty. Even in a perfectly empty void, quantum fluctuations, tiny ripples in the fields, never fully disappear. And over a long enough span of time, a stretch so vast it makes eternity feel short, those fluctuations could, in principle, spark another Big Bang. Not because of a purpose. Not because of a plan. Simply because in infinite time, even the most improbable events can eventually happen. A new universe could bubble out of nothing, just as our own might have done. And if it can happen once, it could happen again. And again. Forever. Some physicists call this the oscillating universe, the idea that reality moves through cycles of birth, death, and rebirth, each cycle lasting a duration beyond anything we can meaningfully imagine. We would be living in one such cycle, completely unaware of the ones before or after. Another idea involves the multiverse, the notion that our universe is just one among countless others, each with its own laws of physics, its own history, its own fate. Some universes might be brief, collapsing only seconds after they appear. Others might expand forever, just as ours seems to be doing. And some, just a few, might have the right conditions for stars, planets, and life. We happen to live in one of those lucky ones, not because we're special, but because only in such universes could anyone exist to ask the question. These ideas are beautiful in their own strange way. They suggest that the end might not truly be the end. That maybe, in some deep sense, the universe finds a way to continue, to renew itself, to begin again. But honestly, we don't know. These ideas lie far beyond anything we can test today. We can't observe other universes or watch cycles of rebirth. All we can do is speculate, calculate, and wonder. And maybe that's enough. Maybe the answer to what happens at the very end matters less than what we choose to do with the time we have. So take one more deep breath. Feel the weight of all this, the vastness of time, the unimaginable distances, the sheer impermanence of everything we know. Let it wash over you, not as a burden, but as a reminder. A reminder that you're alive in a rare moment. That in the tiny space between nothing and forever, there is a window where stars shine, where planets form, where life blooms, where consciousness appears to marvel at it all. You are part of that. A particular arrangement of atoms that will exist only once, for a brief moment, before melting back into the cosmos. But right now, in this moment, you're here. Aware. Alive. Connected to everything that came before and everything that will come after. The atoms in your body were forged in stars. The oxygen you breathe was made by trees grown from sunlight. The water inside your cells may once have been clouds, rivers, oceans. You're not separate from the universe, you're made of it, a temporary expression of a far larger process that is telling its own story. And the ultimate fate of the universe, whether it's a cold heat death, an endless loop of rebirth, or something far beyond our understanding, doesn't diminish the meaning of this moment. In 100 trillion years, the last star will flicker out. In 10 to the power of 100 years, the final black hole will evaporate. But right now, tonight, you're here. And that is a miracle. The dark futures we explored, the death of the sun, the rise of artificial intelligence, climate change, asteroid impacts, the final fading of the cosmos, they're all real possibilities. But they are distant, almost beyond imagining. What they offer is not fear, but perspective. A way to see our lives against the wider canvas of cosmic space and time. They remind us that nothing lasts forever. That everything, stars, planets, civilizations, even universes, has a beginning and an end. And between those points, there is life. There is experience. There is beauty. They remind us to cherish what we have while we have it. To be kind to each other, because we're all sharing this impossible, flickering moment. To care for our planet, because it's the only home we have. To stay curious, to explore, to learn, because we're lucky enough to be alive at a time when such things are still possible. And they remind us that the end, when it comes, doesn't have to be frightening. It's simply part of the cycle. Everything changes. Everything transforms. And in that transformation there is its own kind of beauty, the beauty of impermanence, of becoming something new, of belonging to something larger and longer lasting than ourselves. So as you drift off to sleep tonight, know that you're held in the arms of a universe that has existed for billions of years and will go on for billions more. That the atoms making you will continue, in other forms, as part of that story. And that this brief moment of consciousness, this little spark you call you, is a gift, a window through which the universe looks at itself in wonder. Rest in the understanding that everything, in the end, is all right. That the future, whatever challenges it brings, is still unwritten. That every ending is a beginning in another form. And that in the vast sweep of cosmic time, this quiet moment, right now, right here, is exactly where you're meant to be. Breathe gently and deep. Let your thoughts fade like morning mist. The stars above will keep shining whether you watch them or not. The universe will continue its ancient story. And you, for now, can simply rest. Sleep well. And know that you are part of something beautiful.